We're going to ramp it up a little bit for this packet, but honestly not a whole lot. Basically, every year that I've taught this, we run out of time. So we usually spend more time on circles and solids, revisit constructions, but transformations is always a real quicksy. So this is kind of typical. All right, transformations. In general, when we talk about transformations, we have translations, reflections, rotations, and dilations. You've actually had these words before. Your translation is a slide. So anytime you take something and you slide it on the coordinate plane, that's what we're going to call as a translation. And it's fun, of course, that the SL in translation matches up with the SL in slide. And that helps us remember. We can slide things left, right. We can slide things up, down on the coordinate plane. And we can also slide things on a diagonal. So anytime that we're just shifting the coordinates and sliding something over. When we have some kind of reflection, of course, the FL in reflect and the FL in flip will tell you, will help you match up those ideas. And your flip is traditionally when you take something and you flip it across a line. So if you take your hand right now and you flip it over, that's what we're talking about. The difference between take your hand and slide it, shoot left, right, no big deal. Take your hand and flip it. Notice the direction your thumb is pointing in changes when you flip. The direction your thumb is pointing in does not change when you're sliding. When we talk about rotations, we're talking about turns. And there's a couple kinds of rotations. One is going to be if you're rotating something about the origin. We can talk about that kind of rotation. And we can also talk about rotating something on a point. So if you want to picture like a shape rotating around one of its vertices. Those are the harder ones. We don't do them as much. Usually we're rotating around the origin. When we talk about dilations, we talk about reductions and enlargements, and we kind of already talked about this when we had all of our conversations about scale factors. So when we talked about dilations, we already talked about all of our scale factors. This is if our scale factor is less than 1, it's a reduction. If our scale factors are greater than 1, that's where we have a dilation as an enlargement. So this is a word that I guarantee you haven't heard of, isometry, and that comes from isometric conversations. Basically, anytime you have a figure on a coordinate plane and you translate it, reflect it, or rotate it, if it's congruent or the same size as the original, we call it an isometric transformation, or we say that's an isometry. And we also call it rigid, meaning that the size and shape of the figure does not change. So size and shape does not change. Out of all of our transformations, translations, reflections, rotations, and dilations, dilations are the only one that produces an image that's similar, but is not isometric. So translations, rotations, and reflections, those are rigid and isometric. Dilations are not. Every time I make a new figure, I call that my image. And my original figure is going to be my pre-image. So we have lots of definitions that we can talk about here. I'll give you a minute to read through them. Maybe highlight, circle, star, any of those vocabulary words that are new to you. Kind of talk to your text and do what you can to help you remember them. I'll give you a minute. Go ahead, read. So then down here on the bottom, we can talk about each type of transformation. So if I'm taking this block and I'm sliding it from one direction to the other, what would I call that? Yeah, so that would be a translation because it's a slide. It's a slide, left, right, and notice this box doesn't change, it's the same size. How about my story with my arrow? What would you call this one? Yeah, so this is a reflection over this line. So if we have this line of reflection, what's interesting is you'll see that the same distance from each individual part, that remains consistent. So when we talk about a reflection, thank you, grab a packet. That's that reflection over that line. And each individual point is going to be the same distance on the opposite side of the line as its corresponding point. So this point and this point are going to be the same distance across the line. Hey, good morning. Thank you. All right, so if that's our translation and reflection, what is this guy? And with our rotation, we can see that it is being rotated a lot around some point. So you can take and you can talk about the angle of rotation by looking at what it is this angle. And you can see that this is a 90-degree rotation. And sometimes when we talk about rotations, we talk about clock or counterclockwise. So clockwise is going to be that same direction that the hands travel around the clock. So if you were to draw that angle, you can talk about what degree is. All right, so would you call this dilation down here on the bottom, would you call it a reduction or an enlargement? So if you know this is your pre-image, and you know this is your image, that means that this came first, this came second, this is smaller. So yes, it's a dilation, and we would call it a reduction because my scale factor is going to be less than 1 and making it smaller. Sound okay? All right, let's take a look at the next page. All right, so transformations need labels to distinguish which is the pre-image and which is the image. And we do that by adding a prime symbol to name our image and its corresponding vertices. So if my pre-image is A, then my image is going to be A prime. And that's how we would say that, A prime. In the graph below, the transformation is a reflection over the x-axis. Use arrow notation to describe this transformation. Our triangle RST is transformed to triangle R prime S prime T prime. And we can say that it's mapped onto or it's transformed onto it. So what ends up happening is we can go ahead and label the corresponding. If it tells us it's a reflection over the x-axis, that means that this shape has been reflected over this axis. So this vertex here is going to correspond to S. This vertex here is going to correspond to T. And notice R is the, oops, just one tick. R is the furthest away from that line of reflection each time. So if RS was rotated, that means that our image of it is going to be R prime, S prime. If you're asking me what the pre-image is of segment R prime T prime, that would be segment RT. We do have the ability to do a second transformation, and we would call that a double prime. And we can have a third transformation, and we would call that a triple prime. We can have a fourth transformation, etc., etc. All right. Would you please map a second reflection of this triangle over the y-axis? So here's your y-axis here, and now what they're asking you to do is flip this triangle and map it, and then you're going to name it with the double prime symbols. Go ahead, take a minute and do that. Go. All right, so as you can see, RT flips this way, and then we can have this triangle flip this way. And notice how where here R is the furthest from the axis, now S is. He has the furthest to go as he's flipped over. All right, down here on the bottom, we have some exercises which you and your group work through these 10 problems now together on your market set. Talk and say, let's go. All right, so let's talk about these. What is this happening here? Yeah, this is going to be our rotation. How about this? Perfect. How about this? All right, so use a graph for the transformation below. A, B, C, D is the pre-image. That means this came first. So when we talk about A, B, C, D, and you're talking about what it maps onto, if you're looking at what happened here, do you agree to me that this looks like a rotation around the origin?
Oh, you can't say reflection transformation?
So did you reflect? Right? You could have. So what's interesting is a lot of times what I'll end up doing is I'll end up getting maybe a little post-it note and reenacting what I see. Do you see this here? And now when I want to rotate him around, do you see him there? Now maybe what you did was you went this way and you flipped him over the x-axis. And then did you flip him over the y and then the x? That might have been possible, right? So there's two different options you have here. But at the end of the day, you know that vertex A corresponds with vertex E. And B corresponds with F. And C corresponds with G. And D corresponds with H. You okay with that? Yeah. So I said it was 180-degree rotation around the origin.
You have to add the 180 degree every time?
Typically it helps you so you know how much the rotation was. So you let everybody know what the rotation was. If somebody else said, I said it was a reflection over X and Y axis, it would have worked out fine. In fact, we're going to talk about that at the end of the packet. That's called a composite transformation, where you combine two of them together. All right, so the image of CD is going to be GH. The pre-image of FG is going to be BC. The coordinates of the pre-image of point H, 1, 2, 3, 4, 5, 1. Sketch the image that results when figure ABCD is reflected over the x-axis, followed by a reflection over the y-axis. So reflected over the x-axis is going to look like this, because it went over the x-axis and then over the y-axis. There you go. All right, number 10, find the value of each variable given that the transformation is an isometry. This is one of those vocabulary words where once somebody tells you, oh, that means that they're congruent, now you can answer all these questions. Because 3 times A is going to be equal to 138, and B is equal to 95. And 2 times D is equal to 7. So D is equal to 7/2 or 3.5. A is equal to, what's that, 46? Do I have that right? Check my math.
Yeah.
And then B is equal to 95. That's one of those SOL questions that once you remember what an isometry is, then you have every shot of getting that problem right. Until you know what that means, you're guessing. All right, let's go to the next page. So what we're going to do is we're going to talk about each individual one, and our first conversation is about reflections. One type of transformation uses a line that acts like a mirror with an image reflected in the line. Transformation is reflection, the mirror is the line of reflection. A reflection is an isometry, it does not change the size. If the pre-image is on the line of reflection, then the image is equal to itself. If the pre-image is not on the line of reflection, then the line of reflection is the perpendicular bisector of the segment connecting the image and the pre-image. Here's what we're talking about. If this is my line of reflection, then this line that connects the two shapes, number one is perpendicular to the line. Number two, that shape is going to be equidistant from that line of reflection. A figure in the plane has a line of symmetry if the figure can be mapped on itself by a reflection in the line. So there's two kinds of symmetry. We're going to talk about rotational and line symmetry. Your line of symmetry is going to be if the figure can be mapped onto itself by having that reflection. Your body technically has line symmetry. Now I know we're all a little bit off. I broke my finger playing softball, so that's definitely not identical. It's definitely an enlargement. But theoretically, if you fold your body in half, that line of symmetry that goes down, you go ahead and map you one onto each other. It's some minor differences. So that line of symmetry is what you can draw if you can fold the shape onto each other and see that. All right, so what we want to do is take a look at all these shapes, and we want to draw all possible lines of symmetry in the shapes below. Talk about it with your friends. Go. So when we draw these lines of symmetry, what we want to picture is if I folded that shape in half on that line, would it map onto itself? So if I draw a line like that and you pictured that being a fold, would that map onto itself? What's interesting is with this regular shape, this hexagon, I can draw 3 lines of symmetry where it's folding onto itself. But then I have to ask myself, wait, can I fold it on the corners too? So if I folded my hexagon this way, are these lines of symmetry too? So how cool is that? The hexagon has 6 lines of symmetry, whether I'm folding it on the vertex or on the side. That's kind of cool, right? Hey, what's this shape? Say it out loud. 1, 2, 3. It's a quadrilateral. It's a parallelogram. You're like, how do we know? It looks like one. Did anybody find any lines of symmetry on the parallelogram?
Yes.
There's no way you could fold a parallelogram and have it be mapping onto itself. And this is one of those ones, again, where sometimes it's worth getting a piece of paper and cutting and seeing. So I'm going to take what I think looks like a pretty good parallelogram. We're not going to measure. I'm going to pass it to Olivia, and I'm going to say, like, you let me know if you can fold that any way onto onto itself. Because you think you should be able to. Now, the parallelogram has rotational symmetry. We can spin it, and it'll map onto itself. How about our trapezoid? Yeah, if we're sure that it's isosceles, and we might need a little bit of more information, but if we're confident that this is a story that we can handle, then we can say yeah. And of course, this is none. And this is line symmetry. So I gave you a bunch of things that I saved each year from a calendar that we had, and they show you the difference between rotational and line symmetry. So there should be at least one for every person in the group. Pass them out so everybody has one. And what I want you to do is determine whether it's line or rotational symmetry. And I got bad news for you. My kids like, oh, look, we can fold it in half, so they did. So here's a hint. If it's folded in half. Spoiler alert. If there's a crease down the middle. But try to fold it both horizontally and vertically to see if it works. Most of them were really cool. Have any of you read the Da Vinci Code? So years ago, a book came out, I forget the name of the author, something Brown. Really cool book called the Da Vinci Code, where it goes on this. Have you seen the movie National Treasure?
Oh, yeah.
Like, so they made National Treasure, and it was a really famous adventure movie, more for kids, but it was based on the same concept as the Da Vinci Code. And it goes through looking at all these historic clues and whatnot that go on this treasure hunt. And the clues almost all are these rotational and line symmetric things where the words all say something that can be spun, and some of them are kind of cool for sure. I think the answer's on the back, so a couple of them, if you can't read them, don't be afraid to flip on the back. All right, so when we're asked to draw a line of reflection in line L, this is the easiest way that I know how to do it. Are you ready? Each point, remember what we said, each point is going to be connected by a perpendicular bisector to its corresponding point. So if I draw something that's equal distance away, that makes it easy for me to draw. So if I think about this point coming all the way down, being about this far, maybe a little bit more, and this one coming down to maybe this far, then I've got 1, 2, 3, 4. So then you could go ahead and draw that shape as a reflection because of that relationship of the imaginary line connecting them. It's a little harder when your line is crooked, so sometimes I cheat and I make my paper crooked so my figure is straight. And then I go ahead and I'm like, okay, so that's that vertex. And that's that vertex. And if I go across the same distance, that's that vertex. And if I go across the same distance, that's that vertex. So when I look at that reflection across a diagonal line, I can still see that relationship. Kind of cool, yeah? So I love this one. It's the simplest of what we can talk about, but it drives home one point that I guarantee everybody missed. Ready? Reflection in the y-axis, and when you're hearing the word in the, you can talk about over, because that reflectant is reflected in the x-axis. So if it's this far away, we'll call that, then we can go ahead and say it's this far away. So if we call this A, we'll go ahead and call this A prime, because it's reflected in the x-axis. The reflected in the y-axis is the one that's the tricky one, because if this is my line of reflection and I made this point nice and big, guess what? It's its own image and pre-image. So that takes us back to this conversation up here. If the pre-image is on the line of reflection, then it's itself. So we kind of scooted past that, and whether or not you're like, I don't get that, can you go over it? Here's an example here. Because if I'm reflecting this over the y-axis, it's sitting on the line of reflection, so it's itself. When I talk about the line y is equal to x, that is a linear equation with a slope of 1 at a 45-degree angle. So when we talk about the line y is equal to x, that's where x and y have the same coordinates. 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, -1, -1, -2, -2. So this line, y is equal to x, is this diagonal at the 45-degree perfect slope of 1. That's our basic parent function for all linear equations. So when we talk about this guy's reflection, this point, if I draw a perpendicular line that's bisected, its reflection we'll call this A triple prime. This one was A double prime, where it was itself. And that's one of those basic questions where once somebody shows it to you, you're like, oh, I get it. And then you get that question right on the SOL. If somebody hadn't shown it to you, you'd been like, I don't get it. Are we feeling good? We okay? Good?
So when you put like the primes on, is that 3 for the triple?
Yeah, I just showed that as my third because it's my third problem here.
Okay.
Yep. Just to distinguish it from the other ones.
Okay.
Sound okay? And for you. All right, find the coordinates of the reflection without using a coordinate plane. Then check your answers by plotting the image and pre-image on the coordinate plane. So what we want is for you to think about how this is reflected. And as far as this whole without a coordinate plane, go ahead and use it. It makes it easier for sure. So with your partners, work on 4, 5, 6, 7, and then go ahead and come down here to this page. And I want you to find the name of segment 1 after that reflection. So take some time and work on this with your group mates. Go. All right, so check out my drawings. What I tried to do with my yellow pen is to show you each of those different lines of reflection. If I talk about my original point M at over 3 up 4, when I'm reflecting it in the horizontal line, y is equal to 1. So M was 1, 2, 3 above. Now it's going to be 3 below that line. So there's all kinds of mathematics formulas that you can have. If you look at the y coordinate, the difference between 4 and 1 is 3. So then when you go 3 below 1, that's how you get -2. Go ahead.
Why, when it says y1, why did you, do it in like the direction of the y-axis? That makes sense?
Because when you're doing a horizontal line, and when I used to teach algebra, we would talk about a horizontal line as a HOI. A horizontal line has a slope of 0 and just y's. So that means that y is equal to 1 no matter what. So it's kind of counterintuitive because your y-axis goes up, down. But when you have a y is equal to equation, that means that no matter what the x is, your y is always equal to 1. So a hoy is always going to give you a horizontal line where your y value is constant.
Okay.
So your horizontal lines are hoys. Your vertical lines, anybody know what we call them? Yeah, your vertical lines we call a vux. We say that's a vertical line with an undefined slope and an x. So when I would teach algebra, we would talk about hoys and vuxes all the time. Because your vux is where x only is allowed to equal to -3. Well, that's this line here. So when I look at my x coordinate, P is 1 greater than that line of reflection, which means my image is going to be 1 less than that line of reflection. Notice my x, y stay the same. So there's all kinds of formulas and patterns that can go with these. In fact, if you flip your packet to the very, very, very last page, you'll see an example of some of the formulas. Very, very last page. So that kind of stuff gives me a headache. I would rather not do it. I'll show you what I'm talking about. This very last page is this kind of stuff. I don't remember this. Memorizing this, I don't know, I'd rather go to the dentist than memorize this, right? So to me, it makes sense just to understand the relationship between what ends up happening. Okay, let's take a look at n. -2 up 2 is reflected in the horizontal line. It's a hoy. So when I look at my y coordinate, I'm 3 away, which means my pre-image is 3 above, my image is 3 below. My x coordinates stay the same. I'm going to talk about q. It's reflected in this vertical line. X is equal to 3. If my x coordinate is 2 greater, that means that for my image, my x coordinate is going to be 2 less. So when you see it on the coordinate plane, so what they wanted you to do originally is apply these rules without the coordinate plane. As far as I'm concerned, if life gives you a coordinate plane, use it. So if it's easier for you to do it like that, then please do. This is one of my favorite questions. In fact, I've stolen this graphic and used it on quizzes and tests or whatnot, and just changed what the questions are asking. Because if I'm talking about a reflection in the x-axis, a reflection over the x-axis puts me at 7. And it all is with respect to segment 1. And these are all individuals, but you can have a good time with multiple transformations if you take one, like they do here in 12 and 13. And their whole point in here is if you have a reflection in the x and y axis, it doesn't matter what order you go in, x and y the next, but that's going to be the same as a reflection in the line y is equal to x. I think that's pretty cool. Some of us are really good at flipping these things around in our head and seeing the image and pre-image. Some of us struggle. If it helps to add color or draw it or spin your paper, please do. Sound okay? All right, next tip. Now we're going to talk about rotations. So when we talked about rotations and rotational symmetry, most of the pieces of paper that I passed out to you with that rotational symmetry is 180-degree rotational symmetry. We can measure it by looking at the angle that it takes. So a rotation is a transformation in which a figure is turned about a fixed point, the center of rotation. Rays drawn from the center of rotation to the point of its image is called the angle of rotation. So we can talk about what's happening and how far it's being rotated. Rotations are isometric. If the figure can be mapped onto itself by a rotation of 180 degrees or less, they call it point symmetry. So one year, the SOL, the kids came back from it and they were like, what is point symmetry? What is point symmetry? And I had to go look it up. They added it to the SOL, and I don't know why. So every year I want to make sure you understand point symmetry is where it's an angle of rotation of 180 degrees. All of the little diagrams that I gave you that have rotation are 180 degrees. Off you go. Have a good lunch. All right, welcome back. So what we're going to do is we're going to scoot forward a little bit. Turn in your package. I want to show you a couple things, hints on how to get some stuff done, and then I'll turn you loose and let you guys work on this yourself. If you flip the page, these exercises talk about conversations about line symmetry and rotational symmetry. And you can continue doing that. I want to give you a few hints on how to do so. Pop over to question 13. Name the coordinates of the vertices of the image after a clockwise rotation of a given number of degrees about the origin. Here's my biggest hint for you now. This figure right here is in this quadrant here, quadrant 2. If I were to rotate it 90 degrees clockwise, go ahead and take your paper and spin it 90 degrees clockwise. This is what the figure will look like when you graph it. So instead of this being your x-axis, when you spin it, it becomes your y, and here's your x. So your figure is going to sit right here in your quadrant 1. So when you look at it here, this figure right here now is going to be spun and in this quadrant here. So if you work with a partner and you say, okay, I want to spin my paper, you leave your paper as is. Coordinate A is going to be over 1 and up 1, 2, 3. So when you go into quadrant 1, over 1 and up 1, 2, 3, here's where we're going to put point A. Once you get A set, look at the shape again. B is 2 straight up. Okay? Here's A, up 2 is B. Go back to when it's spun. C is up 1 over 1, 2, 3. So we can come back here. C is up 1 over 1, 2, 3. Then, of course, D is 1, 2, 3, 4 down from C. So that rotation, 45 or 90 degrees around the origin clockwise, is going to result in A prime, B prime, C prime, D prime of that original shape. So the spin your paper tactic turns out to be a very helpful one. All right, I want to talk to you about one more thing before I turn you loose, and that is I want to come over to section 4 translations, and I want to introduce you to the idea of a vector. If any of you ever watched Despicable Me, you know vector has direction and magnitude. Oh yeah. And it's represented by an arrow drawn between 2 points. Vector notation can be used to describe the same movement, and they have what we call these angle brackets. They're not parentheses. They are parentheses with a point. We can call them angle brackets. So just if I'm talking about this vector here, PQ, my horizontal component of PQ is 1, 2, 3, 4, 5. My vertical is 1, 2, 3. So when I represent PQ as 5, 3, I know that my endpoint is going to be 5 units horizontally, 3 units vertically away from that start point. So with each of these vectors, you can go ahead and represent this vector here as having a -1 horizontal movement and a 1, 2, 3 vertical movement. So you're writing that in what we call component form. And you start at the tail and you go to the tip. So for example, if I wanted to do this vector here, I'm going to have a positive horizontal movement, 1, 2, 3, 4, 5, and a -1, 2 vertical movement. That's going to be vector form, component form. So down here, when they have you drawing triangle ABC and then translating it, you're going to be moving each vertex 5 to the right and 3 up. And that's that vector component form. Okay?